Okay, so I think we can start again. So hi, everyone. So first of all, I would like to thank the organizers for inviting me to give a presentation here. Uh, I work here. My name is Aris. I work at the University of Edinburgh. I'm a lecturer in the School of Informatics. And I think this is actually a great initiative, and it's so good to see all of you here. So hopefully this goes on for many years to come, I'm hoping. And yeah, as a lecturer, actually this year I'm teaching a fourth-year course, also a master's course, which is called Algorithmic Game Theory and its Applications. And this talk today will actually be about algorithmic game theory, and more particularly about its applications, one of its biggest applications, which is that of auctions or auction theory. So we'll talk about auctions, and we'll see how game theory can actually help us when analyzing those auctions and trying to understand how we should, how bidders should act in those auctions. So let's see, what is an auction? So an auction, let me get this out of the way. So an auction is a mechanism for buying or selling goods or services by means of eliciting bids from a set of interested people, right? For example, a classic example is if we have a painting or a piece of art and we would like to auction that out. For example, this painting here. This is usually what comes to mind when you think of auctions, but actually the most prominent example these days is something called ad auctions. So these are auctions for selling advertising space, and we call those ad impressions, on online marketplaces, which we call ad exchanges. And most major companies have some of these online marketplaces. So there is a Microsoft exchange, a Google exchange, Facebook has an exchange, many others. And they're selling advertising space on these exchanges. A lot of companies are participating, buying and selling. And as a matter of fact, this is a multi-billion dollar industry. So in 2022, this was nearly 60% of Google's revenue, which is more than 160 billion. So it's a lot of money that is being made via auctions. So what about the theory of auctions? The theory of auctions aims to understand how rational, or as we call them, self-interested parties, let's say people or companies that participate in those auctions, how should they bid? So this is what we're trying to understand via the theory of auctions. And that was initiated back in the 1960s in a seminal paper by William Vickrey. Here's William Vickrey. And then there were a lot of seminal works that followed over the years in the 70s, the 80s, the 90s, thousands, and still up to this day. Many of those works resulted in multiple awards like Nobel Prizes. And here are some people that won those, like Roger Myerson, Paul Milgrom, and Robert Wilson. And there are many other great people that worked on this topic. And an integral part of auction theory, as I mentioned, is game theory. So game theory is actually what underlines this the theory of auctions, and we'll talk about this today. And game theory, in turn, was founded in the pioneer works of people like John von Neumann and John Nass back in the 1950s and even earlier than that, and of course, many other people. So what is game theory? So it's hard to have just a definition, one definition. I have this definition, which I borrowed from Kusha, who has been teaching the course for many years. I don't know if it's his or somebody else's, but we can say that game theory is the formal study of interaction between goal-oriented agents or players. Sometimes we call them rational or strategic agents, and the strategic scenarios that arise in such settings. And if we try to instantiate that in the context of auctions, we will get a question like, how should these rational strategic players choose their bids in these strategic scenarios that we have in auctions? I'm in an auction with a bunch of other people. How should I choose my bids? Okay, so I have a little thing that we can do together here. Here's the scenario, okay? Completely hypothetical, by the way. So the course coordinator for the fourth year MSc course, Algorithmic Game Theory and its Applications at the University of Edinburgh just prepared the exam for the course this week, but his salary has not kept up with inflation. So he decided to sell the exam out to the interested students. Don't tell anyone. And you're willing to spend up to a certain amount of money to buy this exam, between 0 and 1,000. You might be taking the course this year, so it's perhaps worth a lot to you. Maybe you're not taking it, so maybe it's not worth that much. But just to fix things, you can paste this if you have a phone or a tablet or something. Just paste this there and you will get a random number. Look at this number, but don't show it to anybody else. Just remember it. This is your number. And while you're doing this, let me explain what we're trying to do. So what you're trying to do here is to maximize what I will call, for now, your happiness. And your happiness would be the amount that you're willing to spend, which is the number that you will get from this random generator, minus the actual amount that you will spend. Okay, so you're trying to maximize the amount you spend, rather the amount you're willing to spend minus the amount that you spend. The item, if you don't win to spend anything, you'll just get a 0. Your happiness will be 0. And the rule of the auction is that the highest bid wins, and the payment is that bid. Okay, so that's the rule of the auction. Again, you're trying to maximize your happiness. Try to remember this slide. And then let's get some answers in. So I have prepared a little thing here. All right, so what you can do, oh, do I need to change the, oh yeah, you can see it. Okay, that's great. So you can paste this thing. So go to wooclub.com, use this code, and just write the number there. Just write your bid there. So you got a random number, decide what you're going to write there, and we'll check the answers in a second. Actually, you shouldn't be saying this. So let's, yeah, just do it. Just write it there. The code, I can tell you the code quickly without looking at it. So what was the code? The code was EZERDG, EZERDG. Okay, keep voting, keep bidding, and we'll get back to that. Let's continue a little bit. Oh, this is not great. So why is it like this? Okay, so this auction that I described in the previous slide is what we call the first price auction. So actually, this auction is being used to buy or sell a house in Scotland. So these are houses in Scotland are sold by what we call sealed bid first price auctions. How does that work? Each bidder submits their bid independently. They put it in a little envelope. Nobody else sees it. The winner is the bidder that has the highest bid. And then something that I didn't specify, but actually if there are multiple bidders that have the highest bid, then we choose one at random. You can do that. And then the winner needs to pay that bid, whatever they bid. Otherwise, if you don't win, you don't pay anything. So this is a first price auction. It is being used if you want to buy a house in Scotland. A little bit more formally, let me define this auction. So there's a set of bidders, n bidders, 1 up to n. There's one item for sale. And actually, generally in auctions, you might have multiple items for sale, but today we will only talk about auctions for which you only have one item for sale. And every bidder has a value for the item. This is the willingness to buy that I mentioned before. This is the number that you got from the generator. So this is how much money you would be willing to spend, let's say, in the auction. And we call this VI, that's the value of bidder I. And then every bidder needs to choose a bid. And your bid doesn't necessarily have to be your value. It's a function of your value. So given a value, you need to choose a bid in the auction. And then we have this set W. So what does that mean? Well, basically what this thing is saying here is that there is a set of possible winners. All the people that have the highest bid, this is just the set W. And then the utility or the happiness, so we call this the utility of the bidder, is the value minus the bid. And this is scaled by the number of possible winners if you were one of the possible winners. So think of it as follows. There are a bunch of people that might win the auction, 10 people with probability 1 over 10, I will be the winner. In that case, I will pay my bid, but I will get my value, so it will be VI minus BI. And if I'm not among the set of winners, then I get utility 0. So this is basically the formal setup of the first price auction. How should you bid? So let's go to WooClub and let's see what you guys did. Okay, so I have a bunch of numbers here. 878, 972. I have a 972, 990. Okay, there's 1,000. I will ignore the 1,000. Okay. Okay, so does anybody want to share the thought process while bidding this? Not necessarily the person that won, anyone. Do you want to share your thought process? How did you decide to bid here? So you have the number, right? So you got, what was your number? 9072, and you bid 9072. Okay, that's one thing to do. Meet me outside and you can give me that money. Any other thoughts? That's certainly one thing you can do. Any other thoughts? So what is your happiness? Let's say if your willingness to buy is 972, let's say that you win the item. What is your happiness? 0. Is there any way to get more happiness than that? Bid lower, okay? How much would you bid? What was your number? And what did you bid? But even if you won, your happiness would be 0, right? Is there a way to get more happiness? You can try to bid a bit lower than your value, right? But what's the problem with that? You lose, but do you know that you lose? It's not clear, right? You can have you can probably think that, well, with 360, there's a bunch of people here, probably you're going to lose. But in any case, let's think about this. So what is the right way to bid here? It's not entirely clear, right? So let's see. One thing you might be thinking, so this is a valid way of thinking. I should bid lower than the amount I'm willing to spend to win the item on sale for a smaller price, right? My happiness will be positive if I manage to win it. So maybe I should try to bid a little bit lower. I shouldn't bid my value. But again, I shouldn't bid too low because then I'm going to lose this item. There are other people here. Presumably somebody has a higher value. So if my value is high enough, I still want to win it. It's just I want to make the price drop a little bit. How should I bid, right? So it's not clear exactly what you have to do here because basically you have an expectation about what other people are going to do, but you don't know. You don't know the values of the others. We'll come back to that. Before we try to answer this question, let me ask another question. Can we design a different auction that doesn't really require us to think like that? Can we design a different auction that says, okay, I don't really have to think about other people, what they're going to do. I don't care about my, I don't have to estimate what other people are going to do. An auction that is easier to participate in. So there is such an auction, and it's called the second price auction, and that was also defined by Vickrey in the same work in the 1960s. Again, here we submit the bids independently. The winner is again the bidder with the highest bid. And then again, if there are multiple winners, possible winners, we choose one at random. But here, the difference is that the winner does not pay their bid, but they pay the bid of the second highest bidder. Not the highest bidder, the second highest bidder. And if you don't win, you don't pay any. Okay, so that's a little bit different. So let's see what happens when we do that. Let me give you an example. Let's try to work out together how we should bid in this auction. Assume that you have a value, so your value is 5. Okay, so that's your value. This is the number that you got from the generator, let's say. So there's your value. And let's assume that this is the highest bid. If you were to bid 5, that would be the highest bid. And the second highest bid would be 4. So the second bidder bid 4. So currently, if you tell the truth, if you're going to bid your own value, then you would get a utility of 5 minus 4. That would be 1. So you would get a utility of 1. Are you better by bidding larger than 5? So here, what do you think? Would I get higher utility? Yeah. Okay, so why would I get higher utility here if I bid more than this? Let's say I bid 6. What is my utility? It is 4, yes, but what is my value? My value is 5. So my utility is always my value minus how much I pay. If I bid 6, I'm still going to pay 4, like before. So my utility is going to be 5 minus 4. It will be 1 as before. So if I bid here, I still win, but I pay the same price. So, but there's no other one. I'm just saying the second one was 4, and this is just me. Yeah, it counts. Yeah. But yeah, so okay, I should specify that this is the highest one and this is the second highest one. There's nobody else bidding anything here. Yeah. So if I bid anything in this region, that doesn't make me better. I cannot get a higher utility. Because I still win, but I pay exactly the same amount as before. The utility is 1. What if I bid below 5? What if I bid here? What is my utility? Is it lower than 1? Actually, if I bid here, again, I have the highest bid. So I'm going to win the item, but I'm going to pay 4. So again, I win the item. So I get VI minus how much I pay, which is BI. So again, I get exactly the same utility. Utility is 1. What about this case where I bid below the second bid? What is my utility then? 0, because actually I don't win the item anymore. But my utility was 1 before. So in any case, whatever I do, my utility is not going to be larger than 1. And if I just tell the truth, if I bid my value, my utility is going to be 1. So I have no reason not to bid my value. And also, you can verify quickly that let's assume that the value is 5, but this is not the highest bid. So there is a higher bid, which is 6. Again, the only way to affect your utility is to win the item. If you don't win the item, then you would get a utility of 0, which you already get. But to win the item, you would have to bid here. But let's say you bid something like 7, you would have to pay 6 because now 6 is the second price. And you pay more than your value. So you don't want that. You would have a negative utility. So in any case, it doesn't make sense for me to do anything rather than tell the truth about my utility. And this is what we call a truthful auction. Okay. So in the second price auction, the bidders do not have any incentive to bid anything rather than the actual values. When you get a number from the generator or maybe from whatever nature, this is your willingness to buy, it's just okay to just submit that number. You don't really have to think about other stuff. And we call this a truthful auction or an incentive compatible auction or strategy proof auction. These are all valid terms. Let's call it truthful for now. And this was actually proposed by Vickrey in the same paper as I said. Now, of course, we have this very nice auction. It doesn't really require people to strategize too much to think about complicated things. But still, the real estate agents, they still use the first price auction in Scotland. So why is that the case? Perhaps they don't really know about auction theory, right? So maybe they're just clueless. But then actually Google and all these other exchanges also use the first price auction. And presumably they're not clueless. Google must know something, right? So there are several reasons for using the first price auction. It's maybe simpler to think about, maybe not simpler to reason within, but simpler to think about. And it has been observed that empirically, it maybe generate better revenue for the platform. Although theoretically it shouldn't, in a sense, but empirically perhaps it generates more revenue. So bottom line, people still use the first price auction rather than this nice second price auction. So we might as well understand it. So it's nice that we have this other auction, but still we would like to understand the first price auction. Now let's try to analyze this. And how I'm going to bid in this auction depends on what do I think about the others. And here's some things that you might be thinking as a student here. The person to my left is taking a GTA. They would probably be willing to spend a good amount of money to get the questions. But the person to my right is a first-year student. They don't care about the questions. It's too early for them yet. So they're not going to bid too much. So how do we do this mathematically? Mathematically, we model the beliefs that that bidders have about other bidders by probability distributions. In particular, for every bidder I and j, there is a probability Fij that captures the beliefs of bidder I for bidder j. So this could be discrete distributions or continuous distributions. So this is the PMF of the distribution, the probability mass function. That would be the density of the distribution in the continuous case. So basically what's happening here, well, this is what I think about another bidder. And I think that with probability 1 over 100, their value is going to be 0. With probability 1 over 5,000, their value is going to be I don't know, something else, 32. With probability 11 over 138, their value is going to be 700 and something, and so on. So these are all the possible things that can happen. These are my beliefs about the other person. And here we can have this continuous that basically says that, we have certain values for any value between 0 and 100, certain probabilities that this thing can happen. So these are two different things that one can study. This is easier to conceptualize, to think about on the left, but there is some merit to also thinking about this on the right. And some simpler, interesting cases. So here is the general case, but there is a very interesting case, and actually one that most of the literature studies, in which these beliefs are objective. So what I think about Kusha is the same as what Rahul thinks about Kusha. Maybe Kusha, maybe we know that Kusha, there is some data to suggest that Kusha is going to act in this certain way. It's going to have values in this according to a certain distribution. So maybe your competitors, maybe there's some historical data or something like this. So it makes sense in many cases to assume that these beliefs are objective, and even actually there are also simpler settings in which these are even symmetric. So all of the values come from the same distribution for all of the bidders. Okay, and then we have the bidders optimization problem. This is the most technical slide that I have, and it's not very technical. A bidder would like to come up with a function, beta, which maps values to bids. So this is what the bidder is trying to do. Given the bidding functions of the others, so let's say all of you have decided to use some bidding functions. I know your bidding functions. I don't know your values, but I know the bidding function. So I know that if your value is 5, you're going to bid 8. I know that. And I also have some beliefs about all of you via these distributions. And then I'm trying to maximize my expected utility. So basically what happens is that for each one of you, I draw a value from the corresponding distribution. And then I look at, your bidding functions on those values right here. And then I can see whether I win or not. If I'm going to win, my value is going to be this. If I'm not going to win, my value is going to be 0. And then I just calculate the expectation of this thing, basically. So this is how you calculate, this is how you come up with your own function. So this is, it's hard to digest at first, I would say, but basically it's just a calculation of an expectation. And then this brings us to the fundamental concept of a Bayes-Nash equilibrium. Imagine that every bidder has come up with such a function. Somehow I came up with those functions, you guys came up with your functions. And then this function maximizes the expected utility of the bidder given the functions of all the others. So in other words, unless you guys one of you is willing to change, I'm not willing to change. Now this set of functions is called a Nash equilibrium, or a Bayes-Nash equilibrium to be precise, but let's call it a Nash equilibrium here of the auction game. And this is John Nash, by the way. Okay, so when each one of us finds a function that we're happy with, we don't want to change, then this is a stable outcome, and we call this a Nash equilibrium. Now, what you might be wondering here is it even possible to do that? Does it even exist? Is it possible for all of us to be happy at the same time in this certain sense? Because in principle, this could happen, right? So let's say that each one of us has chosen their function. So these are all of our functions. And then suddenly I'm thinking, no, this is not good enough for me. I'm going to change to another function because that will give me higher utility. But then Paralabos might be thinking, oh, no, but then I want to change to another function because now you changed, so I would like to change as well. And then somebody else might be thinking, but now I would like to change to another function. And then who knows, changing from function to function, maybe in the end, we somehow end up with where we started from. So is it possible that there's no way in which all of us would be happy with the function that we have chosen, and rather than that, there would be one person that we would like that would like to switch? So in other words, is there always a Nash equilibrium for these games? And the answer is that depends. If the distributions are discrete, what I showed you on the left, then a Nash equilibrium might not exist. And this was shown in a paper back in the 1980s. But if the distributions are continuous, then a Nash equilibrium always exists, which is kind of remarkable if you think about it, but it does exist always. So on the left, we don't necessarily have an equilibrium. On the right, we do have an equilibrium. How would one prove those statements? First of all, the first one, that there is no equilibrium. This is kind of easier to prove in a sense because it suffices to construct an example. Here's an example of an auction. Here are the values. Here are the distributions. And on this example, I can make an argument that it's not possible to have an equilibrium. There's no equilibrium. How do we prove the other one that says that there always exists an equilibrium? This kind of arguments are more complicated and usually involve proofs that go by fixed point theorems or topological lemmas. So this one, for example, uses a fixed point theorem by Brouwer or another one by Kakutani. These are, things that you might not have seen before, but these are general proof techniques for existence of equilibria. And if you're taking the AGTA course, you have seen something like this, or if you'll take it in the future, you will see some examples. Okay, so what is the caveat of the existence proofs? Well, they tell us that an equilibrium always exists. That's great. We have an equilibrium. So we can hope that bidders somehow will find this equilibrium when they play against each other. Somehow we'll end up with this nice outcome that is stable and everybody's happy. But we would like to know more about it. Actually, how does it look like? Can we describe this equilibrium somehow? Can we say something useful about this equilibrium? Let's go back to the paper of Vickrey back in the 1960s. So Vickrey defined the second price auction in that paper, but that's not all he did. He actually described the equilibria of the first price auction when all of the bidders' values come from the uniform distribution. So the uniform distribution is this one, density like this. So basically, everybody has, all the values are equiprobable for everyone. And this is what Vickrey came up with. For two bidders, he established that the equilibrium strategy is to bid half of your value. So if your value is 782, you have to bid half of that, whatever your value is. And if you have more than two bidders, then you get how much you should bid in equilibrium according to this formula. So you have three bidders, it's 2/3. If you have four bidders, it's 3/4 of your value and so on. So before, when I asked you how much would you bid in this auction, if you were to go by the equilibrium behavior, that means that, if each one of you bid this much, then in expectation, you will be maximizing your utility against the utilities that the others have chosen. So if everybody coordinated, let's say, to submit this much, then none of you would like to change. If you were just interested in maximizing your expected utility, let's say. Okay, so what Vickrey provided is called sometimes a closed form solution. It describes the equilibrium in a closed, nice form. And then the literature has managed to produce these closed form solutions for more complicated problems, but still usually in the symmetric case, so in fairly simple settings. And if we go beyond the symmetric case, then we need to be more modest. We should not be looking for these closed form solutions. Sometimes the literature has produced some other ways of describing the equilibrium, let's say a system of differential equations, things like that. But these are not easy to solve. It's not that nice. It's not that easy to figure out what the strategy should be. And often we cannot even get those. So there are settings for which we cannot even describe the equilibrium in such a way. And this is where computer science comes into the picture. Okay. So in computer science, when we're given a problem that we would like to solve, how do we describe a solution? Or let's say a process of finding a solution. Or in other words, what is a sequence of steps that use the input in a way to produce an output that will be a solution? How do we call this thing? An algorithm, yeah? So this is an algorithm. So in computer science, we have algorithms for finding things. And we want our algorithms to be fast. What does that mean? Well, it means typically that we want them to run in what we call polynomial time. So the running time of the algorithm has to be a polynomial function of the size of the input, of the representation of the input. And I will just be calling these algorithms efficient, right? So when I say efficient, I mean that something runs in polynomial time. Okay, so here's a concrete problem from the CS perspective, looking at those auctions. Given a first price auction as an input, can we design an efficient algorithm for finding an asset equilibrium of the auction? So that's the computational question. That's the concrete CS question that we have. Now, I want to tell you that this is more intricate than it looks initially. So there are some things that we have to really be concerned about here. These great people that studied these problems in economics, they were not concerned about computation. Their background was in mathematics, they were economists. They didn't really think about algorithms, let's say. Before we even attempt to design such an algorithm, we need to think about representation. how should we input our parameters of our problem, and what should the outputs be, so that we can use a computer or some abstract model of computation to solve our problem. Right? So how do we describe our problem to a computer, and how do we represent the inputs, the outputs? So this is something that we have to do. So let me tell you how to do this. Existence, I think existence only gets you somewhere, but if you can compute it, then, well, I guess, maybe you can argue about its properties, or, you can understand it a little bit better. Even better if there is an algorithm that, I guess in a sense, you can also think of it as prescribing something to the agents. Like if you're going to play this, you're all going to be happy. But if I cannot find that, then I cannot even prescribe it to the agents. So that's one way to view it. Yeah. Here's what you should be doing. And then, people, if they do that, people will be happy in the Nash sense, let's say. But if I cannot compute that, then, there's no way that I can prescribe this. So for the discrete first price auction, the representation is easy. Okay, for the input, we're giving these numbers in binary representation. These are the values. And then for the distribution, we can just give it explicitly as before. So, for this value, we give the probability. For this value, give the probability, and so on. So for each one of these values, we give the probabilities. And of course, these probabilities have to be rational numbers because we need to be able to represent them. But this is part of the input, so we can do that. So this is fairly straightforward. And the output is also fairly straightforward. Again, the output is a function that says, for this value, I'm going to play this. For this value, I'm going to play this. Now we're in nice finite discrete sets, so we can have this as a map or as a vector that says, OK, for this value, here's the bit. For this value, here's the bit. So that's the representation. Now, in the continuous first price auction, things are a little bit more intricate here. So what about the input? Now, again, we can give these values as part of the input. That's fine. If we have a value, we can represent it. But the problem is that, how do we represent these distributions? Now, these are continuous distributions. So we cannot just say, for this value, you're going to have this probability, right? This is not how it works. What we will do is that we will restrict attention to distributions for which there is a natural representation that we can use. So let me give you exactly those representations. So first, we will assume what we call piecewise constant densities. So basically, this is a function that says that from here to here, I will have this block of value. From here to here, I have this block. From here to here, I have this block. And how do you represent this? For each interval, you can just give the left endpoint, the right endpoint, and the height. So you have a bunch of blocks here, and you can represent every block explicitly. Here's the left endpoint, the right endpoint, and the height of this block. So you can do that. You can either do more general things like piecewise linear densities. Again, you look at an interval. You're saying from here to here, my function is a linear function. So I can represent it by the slope. So I have the interval and the slope, and that completely represents the function. And I could even have more general things like that, like piecewise polynomial densities, where I have these blocks, again, these intervals, but then I have polynomial functions. So once I specify the intervals, then I can just give the coefficients of the polynomial, and then I can represent those functions as well. These ones are actually useful for most applications. They can approximate any kind of function. So you can even just think of constant densities, piecewise constant densities. But we can also do more general things. And by the way, there is a way in which you can represent more general things, even more general distributions. But this is beyond the scope, so I'm not going to mention this. I have some references in the end if you want to take a look. Yeah. Yeah, yeah, the density, yeah. It's a continuous distribution. It's not a continuous density. Now, you can have discontinuous densities and still have existence. We realized very recently that Athei's work actually requires you to have strictly positive density everywhere for it to work. Yeah, yeah. No, no, the equilibriums would exist. You don't need this, this thing that Athei assumes. It's just for convenience. you don't need it. We have a proof via Brouwer in another paper, in one of our papers, for example, so you can do it. But yeah, that's a good point and a subtle point, yeah. Now, what about the output? The output is more tricky, actually. Our functions have a continuous domain, so we cannot just say for every value you're going to get this bit. What does it mean for every value? We have infinitely many values, right? So how are we going to do this? So here, let's have some useful observations. First, we will assume that the bidding space is discrete. This is fine in all applications, basically, because whenever you're dealing with money, there will be some multiples of whatever, some very small quantity, 1 penny rather. So we will assume that the bids come from a discrete set, and then we will also consider a particular case of bidding functions, which are monotone. That means that if I have a higher value, I'm going to bid higher. Specifically, if my value for the item increases or weakly increases, my bid is not going to decrease. This is what it means. And then Athey has proven, and we can also prove it without this assumption of the positive density, that the continuous FPA has Nass equilibria where all the bidding functions are monotone. So we have monotone Nass equilibria. That's great because we can actually represent a monotone equilibria as follows, monotone functions as follows. For every bid, we will specify the smallest value for which the bidder plays that bid. I think it's easier to see it by this picture. So think of it as from 0 to V1, we're going to play the first bid, and then we're specifying V1. V1 is the position where my bidding function jumps from B1 to B2. And then it's B2 for a little bit, and then it jumps to B3, and then it jumps to B4, and so on. And the fact that it's monotone makes sure that we will have this nice increasing kind of step function that we have here. So that way we can actually represent the output of our the output of our bidding function, which are the bidding functions. And we call this the jump point representation. So actually, this was developed in economics. Athey came up with this, or maybe before Athey even. Okay, so now back to the standard computational problem, the concrete CS problem. We managed to find a way, a sensible way of representing these distributions, the input, and also the bidding functions is the output. So it seems that we're all set to try to answer this question up here, but actually the intricacies haven't completely disappeared. So we still have some intricacies to deal with. And this is one intricacy. So what if in every Nass equilibrium, some of these numbers in the output are irrational? So let's say that we find an equilibrium here, and the equilibrium says, well, you're going to switch from bit 2 to bit 3 when the value is 1 over square root of 5. Now, your computer is not going to tell you that you need to switch from B2 to B3 at 1 over square root of 5. Your computer cannot do that because that's an irrational number. So would this happen? Is it just a theoretical possibility? Actually, it could happen. We have shown this in one of these papers. It's well known that it can happen generally in games, in game theory, but it can even happen for these kinds of games. So that's something that can happen, and we have to deal with it. Now, how do we deal with that? Well, we look at the approximate Nass equilibrium. So basically, an approximate Nass equilibrium is a set of bidding functions that approximately maximize the utility of every player. So I'm playing this bidding function against your bidding functions. It doesn't mean that I'm getting my highest utility, but I'm getting almost my highest utility, up to some epsilon. Maybe there is something else that would give me higher utility, but this is just a small epsilon. And the idea is that this is still stable because if I'm going to win, if I'm going to get a little bit more, just a little bit epsilon more, I'm not going to bother, to get into this strategic thinking and consideration. So I'll just accept this bit. Yeah, so this is the epsilon Nass equilibrium, epsilon approximate Nass equilibrium. And the intuition here, and this is not entirely a formal argument, I have to say, but the intuition is that if you get something like this, well, if you look at a nearby point that is a rational number, you're going to get an approximate equilibrium. This requires a proof, but this is the idea. So if we're happy with epsilon equilibria, epsilon can be very small, then we can actually sidestep this potential problem of irrationality. Okay, now we're ready to study this problem. And let's make this question more precise. Recall that if we have discrete distributions, then a Nass equilibrium might not exist. So in that case, what is the computational problem? It's a decision problem. Given a discrete first price auction and an epsilon, decide if the auction has an epsilon Nass equilibrium or not. And if it does have an Nash equilibrium, we would like to find it as well, so we would like to return it. So this is the computational question that makes sense to ask here. And I call this a discrete FPA problem, by the way, because we're talking about the discrete FPA. And rephrasing, what is this problem? So it basically says, if I give you a discrete first price auction and an epsilon, and I ask you, can you design a polynomial time algorithm that decides whether this equilibrium exists? And if it does, it also finds the equilibrium. So this is what I want from you. I want you to tell me, yes, there is an algorithm, or I couldn't find an algorithm. And if there is an algorithm, how are you going to convince me? So if there is an algorithm, what is the evidence for that? So if I asked you, is there an algorithm? And you said yes, how would you convince me that there is an algorithm? What is the easiest way to convince me? Yeah, by the algorithm. So you would give me the algorithm, right? Here's the algorithm, run it, check that it works. I can check that what it produces is an equilibrium, so we can do that. But if you try for a little bit and you cannot find an algorithm, maybe for long and you can find an algorithm, how do you provide evidence that I'm probably not going to find an algorithm? What is the other thing we can have if we cannot have an algorithm? Yeah, so we need a hardness result, basically. Yeah, we can prove NP hardness for this problem, right? If I prove NP hardness, that means that, well, if I could find an algorithm for this problem, I could also find an algorithm that decides 3 sats. And I'm not going to do that unless I'm going to win $1 million US in the process. So we do have one theorem like this in a recent paper that this discrete FPA problem is NP complete. So this problem is NP complete. So we should not expect to design such an algorithm. Now I'm close to the end of the talk, so I'll go over the next slides. I think there's time to talk about this as well. So let's go back to this concrete problem, and let's talk about the continuous case, the continuous first price auction, for which, recall, we argued that an Nash equilibrium always exists. Okay, so let me try to make this concrete. If we try to make it concrete in the same sense that we did before, we could try something like this. Like, given a discrete first price auction and epsilon is an input, decide if the auction has an epsilon approximate Nash equilibrium or not. Now, what is the problem with this? Is this an easy problem or not? Forget about this finding it, just this purple thing. Is this an easy or a difficult problem? What do you think? I need to decide if an equilibrium exists or not. Yeah, say it. It's definitely easier than the last one. Actually, I would say that it's actually trivial because we know that it exists. Here it is. There is a theorem. Some Athey and Vickrey actually proved it in the past. So there is a theorem that it exists. So it doesn't make sense to make a computational problem out of this. I know that it exists, right? So yeah, the answer is yes, and this is trivial. So this is not what I want to do. What I actually want to do is I want to find it. This is different from the fact that it exists. I know that it exists. I just want to find it. So the right computational problem that we can define here is, given the auction and the epsilon, find an epsilon approximate Nash equilibrium. Describe it here, in the way that we discussed how to describe it, before in this, the step functions that we had for the bidding function. So this is the problem here. Now, rephrasing, we can have a similar rephrasing as before. I ask you, is there an algorithm that finds this or not? If there is an algorithm, yes, you can give me the algorithm that says, okay, here it is, it finds the equilibrium. If we cannot find such an algorithm, how are we going to provide evidence that it doesn't exist? Now here it becomes a little bit more tricky because there's something about this problem that is a little bit different from the one before, or different from 3 sats, different from the problems that we know. This problem is what we call a total search problem. A total search problem is a problem for which we're trying to find a solution. It's a search problem, right? So we want to find an equilibrium. It's not a yes or no. I want to find I want to find an equilibrium. So it's a search problem, and crucially, we know that a solution to this problem always exists. So this is what makes it total. Okay. Now, for total search problems, NP does not seem to be the right class, because NP is a class of decision problems, right? And then one can try to think, if you understand complexity a little bit more, you can try to think about whether we could prove NP hardness for these kinds of problems. But again, we don't expect this to be the case. That would break some, some assumptions and complexity that we don't expect to be broken. So it doesn't seem like NP is the right class. NP hardness does not seem to be the right thing. We need a different class, a class that is particularly made for total search problems, like finding an equilibrium here. And luckily, there are, in fact, multiple of those classes. There's a class called PPAD, another called PPA, PLS, CLS, and so on. There are multiple of these classes. And actually, these are all subclasses of a big class that is called TF and P. And I'm not going to tell you anything else about these classes. Many of those were defined by this guy here, Christos Papadimitriou, but also other people back in the late 80s and early 90s. And these classes capture the complexity of several of those problems for which we know that a solution exists, but we need to find a solution. And computing an mass equilibrium is an example of that. Also, what you will hear in the next talk by Alex is also the K-cutting problem is also an example of that. So the relevant class here is PPAD. So what we proved in this first paper that we did is that the continuous first price auction is a PPAD complete problem. So to find the equilibrium is a PPAD complete problem. So what does that mean? For now, just think of it as it's a strong evidence of intractability. So we're not going to have a polynomial time algorithm. This is what PPAD completeness means. Like NP completeness in the same sense, it serves as evidence that we're not going to solve this problem in polynomial time. Now, if you want to learn more about these classes, you can read more about them, and they're a little bit more intricate. Or you can definitely take the course if you haven't. Now, coming to the end, is there any hope for efficient algorithms? Because I showed you 2 impossibility results, 2 hardness results, so is all hope lost for finding good algorithms? But actually, I'm claiming that we're quite far from understanding the computational complexity of the problem, because these hardness results require the beliefs to be subjective. So what I think about, Rahul's values is different from what Kusha thinks about Rahul's values. But if we have objective beliefs, which is the most common case in the literature, then we don't know any similar hardness results. These do not extend. And actually, we don't even know polynomial time algorithms. So the problem is wide open. And we do know some results when the beliefs are symmetric. So we have proven some polynomial time. We have provided some polynomial time algorithms. But again, here I have to clarify that these are algorithms for finding epsilon approximate equilibria. And maybe you can, if they find epsilon approximate equilibria up to a certain epsilon, if we want them to run fast enough. But maybe we can design even better algorithms even for those cases that, achieve better approximations, so to speak. So these are the related papers. So the first 2 ones are the ones that I mentioned. There are some other people that have worked on this topic as well. So yeah, if you want to learn more about this, feel free to talk to me. You can also talk to my student Haralabos, who is here. If I'm scary, you can also talk to him. He's a PhD student. And yeah, so we have written this paper together, and we also have another one that we haven't really included here. We haven't published yet. And finally, just to say that if you're interested, as I said, I will be teaching AGTA, together with Kusha next year, and hopefully for years to come. So if you're interested in game theory, please take this course. You will learn about things like what we talked about today and many more things related to game theory. And also, if you're looking for final year projects next year or the year after that or at some point, feel free to talk to me, and we can, maybe we can find something interesting to do. That's all from me. Thank you. Yes. So the price of anarchy, yeah. So the price of anarchy has been basically settled, if you're talking about let's say the general case. And it's a series of papers, and it's quite complicated, actually. And there is also price of stability result that is not entirely tight. It looks tight, but it's not. There is a subtlety there. But one could ask questions about symmetric equilibrium and things like that in terms of the price of anarchy or simpler cases. And these are a thing open. Mm-hmm. Yeah, so we don't really know any properties about the equilibrium that we compute. And actually, the algorithm is also, it uses an algorithm that solves a system of polynomial inequalities as a black box. So it's not easy to say anything about this equilibrium, rather that it can be computed. Oh, back there first, yeah. Yeah. So when you talk about let's say the welfare of the person that sets the auction, we usually call that the revenue. So this is the revenue of the auctioneer. And there are results that I didn't mention here, but I will mention in the course, for example. So there are classic results from the 1980s from economics that show that if you want to achieve the best possible revenue, here's what you need to do, at least for this first price, not first price, single item auctions. So doing a first price auction is not the best thing you do. There are other things. And also there is a theorem that says that basically, well, informally speaking, at equilibrium, some auctions that are kind of equivalent in the terms of the outcomes that they produce should also give you the same revenue. So there's a theorem called the revenue equivalence theorem, and there is also an optimal auction that extracts the maximum revenue. So there is a lot of literature behind this. Yeah, people have studied this, of course, because people care about, making as much money as possible. Ido, was there a question? Well, okay, so NP would not be because it's a decision problem. So you would have something like FNP or something like that, but maybe that's a technicality. The thing is that if you want to, it's not very difficult to see that if you prove that a problem that is in TFNP is NP hard, that would mean that NP is equal to co-NP. And so we don't expect this to happen. So yeah, and TFNP doesn't have complete problems. Yes, we don't expect TFNP to have complete problems. So we have subclasses of that, and we show complete problems for these subclasses. And it's even kind of more intricate because every one of the subclasses is associated with a different existence principle and a different, let's say, fixed point theorem or different topological lemma. It's kind of, Any more questions? Yep. No, it's not like that. But in a sense, you're right that it's not trivial how to compute, even if you're given the bidding functions of the others and you have your distribution and you want to compute this expectation, depending on the setting, you might have to do something that is a little bit more clever. So for example, in the continuous auction, you have to use dynamic programming to compute what we call the best response. It's not straightforward. Yeah, I kind of did not mention this, but yeah, even this problem requires a little bit of thought, but it can be done in polynomial time. Yes, Khalid. Yeah. So again, the revenue equivalence theorem would tell us that it should have the same revenue as the second price auction. But I think people are not necessarily risk neutral. So they're not utility, expected utility maximizer necessarily. And it kind of makes sense that because people don't necessarily know the distributions of the others exactly, they don't do these calculations. So you can be conservative with your bid, but thinking about the scenario here, let's say you got 700, where you're going to bid, I don't know, depending on how many people there are, but sometimes it seems like maybe people are more conservative in how much they underbid. So you tend to get higher utilities. But this is again empirical and depends on this case. Yeah, Kusha. Oh yes.
Aris kind of cheating also there's different kind of cheating. Let's say the auctioneer, the person who's conducting it, cheats in the following way. They could have some bogus person submit a bid just below the highest bid, right? Just to cash in on. So
yeah.
How do you know that? So you're bidding on a house in Edinburgh. How do you know for a house isn't surreptitiously having take bid, right? That's so it's
Yeah.
to practically realize the second price seal bid auction in a fair way with kind of without pollution, without this kind of cheating is hard to do, whereas first price auctions transparent in that.
More transparent, yes. I guess it's transparency that people are looking after, yeah. Yeah. Yeah, you could. So it depends. So if you have simple settings like the symmetric settings, these results are also usually that the equilibrium exists and is unique. So there are some results that say that it's unique up to things that don't matter, things like that. But if you have more general settings, asymmetric settings, then you can have multiple equilibria. There's no, no uniqueness necessarily. Yeah. Yeah. So there are some other auctions. So there's the English auction or the Dutch auction. So the English auction is like the price increases and then people bid as they go, or the Dutch auction, you start from a high price, or rather, let me see. Yeah, and people start dropping out, something like this. So the English auction has been proven to be strategically equivalent to the first price auction, and the Dutch auction is strategically equivalent to the first price auction. But this again under some assumptions, and there is also this is assuming that you're still an expected utility maximizer and you're not affected by what you see while the auction is being run. But there's also some research that says, well, people don't really know their values, and what they think their values are depends on looking at what other people are doing. So maybe there's some kind of form of correlation there or something like this. So yeah, there are theoretical results about this as well. Yeah. Any last question? Yeah, you have one. Say that again, sorry. Yes. Yeah. I guess the standard assumption is that you have these distributions and we know them and we use them to compute. So one thing is to say, I don't exactly have access to this distribution. Maybe I have some, prediction, let's say, about the distribution. You could do that, but I don't think, this kind of robustness results exist in the literature of auctions. But maybe in some sense, maybe there are some things, but not necessarily in the, the setting of predictions or something like that. That's also distribution, I guess, probability of everything else is 0. So, but then things become easier, Sorry? Okay, then yeah, then I don't know. Yeah, if it could be wrong, then I don't know. Yeah. Yeah, shall we? Yeah. So the person that bid 1,000, please meet me outside.